Good afternoon. Thank you all for being here today. I'm happy to tell you this is the last presentation, so we're almost done. So my name is Joe Chevalier. This is Colin Derby, John Leeser, and Isaac Barker. And our group, as seen here in front of the barn, decided to create a barn scraping, manure scraper for the Green Mountain Yogurt Farm. So this is a simulation of what it looks like. It's an I-beam in the middle of the alleyway. The scraper rides along this I-beam, scrapes the manure out of the barn, retracts on the way back after it hits a switch, and retracts to the other side of the barn where it originated from, shuts off, and sits between the wall to be out of the way. So here's a video of this actually working. You can see a large portion of manure, which it definitely is a large portion for what it generally is, but you can see here that the scraper is doing it seamlessly and leaving a clean path behind it, which would get rid of the need for any shoveling. So this is a picture of the barn itself. So our project, we chose each other, and then we chose this project because we were interested in it and we thought it'd be challenging. So our client, Diane Wyatt, is the owner of Green Mountain Yogurt, the Green Mountain Yogurt Farm, and they've been producing local yogurt for many years now. So this is a picture of her barn, a model of it. The alleyway seen here is what we were meant to scrape out. So they needed this manure scraper because getting the manure from the barn was starting to become way too much of a task that they could handle because they're trying to keep up with the yogurt farm, and cleaning the manure out every morning was becoming too much for them. So our first step in the process was to travel to the barn. This is in Newbury, Vermont. We took measurements, we looked at the layout of the barn, we started brainstorming ideas. How could we come up with a system that would remove this manure and do it effectively? So we looked at the barn. This is the corner where the scraper would start. This is a picture of the alleyway before any modifications had happened. It's Colin looking at it. This is the specification list that we came up with the client. It's basically a list of things that the client expected of us and we expected of the client, which was coming up with how the scraper would work. Some of the outlined ones here, we'd keep a $2,500 budget, which was appropriate because it's much cheaper because any other barn scraper that they could have bought commercially would have cost them $10,000 to $12,000, which is obviously absurd for such a small barn. We completed by April 28th, which we did, and that's today, and it has been installed in the last couple weekends. The scraper will travel at 12 feet per minute, which is safe for the cows because sometimes the cows are standing in the alleyway while the scraper is happening. And the alleyway must be scraped every 12 hours generally. This will make sure that the scraping is done effectively and it doesn't create too much of a load for the motor to handle. So in any project, the most important aspect is design. Problems can happen when you get a project and say, all right, let's just buy some material, start going for it. The most important part is coming up with a plan so you know exactly how you're going to do it and you have your materials laid out, everything you know that you need. So our first decision was, which was the overall method that we'd use to clean the barn. We needed this to be effective. The manure needed to get out of the barn. It needed to be cheaper, and it needed to be durable and long-lasting. So our first, and what we ended up using, was the scraper. This was a good choice because it was durable, it was inexpensive, mainly steel and Delrin, and it was out of the way, it could retract into the wall. The cons were that it could leave trails of manure on the sides, or at the joint here, or it could topple over the top if there was too much manure. And then also the I-beam right here, which would be in the middle of the runway, could be a little obnoxious. Our second option was a conveyor belt, which would be on the floor and the manure would be on the conveyor belt, and then when it was time to clean the barn, they would turn the conveyor belt on and it would take it outside. This would be quiet and it would be low maintenance, but it wasn't really feasible for the barn because of the barn setting. The manure would make it too tough, and it just didn't really work. The third option was high pressure water, which would be, spraying high pressure water through the alleyway. It would be good because it would clean it very well, but it would be dangerous for the cows because it would be spraying high pressure water basically at their feet, and it just wasn't really feasible for the barn. So, as you've seen in many other presentations, we came up with this decision matrix. So here we have our options, the 3 different options, and then across the top, categories that were important to the effectiveness of the scraper or method. So basically each column was scored on 1 to 10 basis. You can see the scraper scored the highest of the 51, basically much higher than the 33 and 31. It was cheap, it was durable, it's all steel, and it was the most feasible option for the barn, whereas the high pressure water, very low feasibility just because of the setting, and then the conveyor belt just across the board, couldn't really find a category where it was really the most effective. Our second decision was picking a drive system for the scraper. So we established, yes, we're going to have a scraper. How are we going to make it move from point A to point B and move it back? So we wanted this to be cost effective. We didn't want to spend way too much money on an expensive motor. It needed to go slow enough for the cows because most motors spin way faster than what we needed them to do. And we needed to be able to reverse direction. Once it got to the back, it could come back and then do it again. So our first option was a motor with a belt drive. So it'd basically be a box with a belt system, as seen here, which would reduce the speed of the motor. The problem with this is it was very complex to design. It's hard to find a good picture of a multi-stage belt system where you have different belts slowing down the spinning RPMs of the motor. But this would be a little more difficult for us to manufacture and assemble, and it'd be difficult to keep clean in the barn setting. And then our third option was a geared motor, or second option was a geared motor, which is what we use. And the biggest pro to this is that the mechanical department donated this motor to our project, which was great for us. And there was not really much work needed to it. So the problem would be, it would be very expensive if it had not been donated, and the electrical control system proved to be pretty difficult for us. Third option would be a hydraulic ram, which would sit on one end of the alleyway and basically push, using hydraulics, all the manure out of the barn and then come back. The problem would be, because it's a long alleyway, that the cylinder would need to be huge for it to get to the other side and come back, and it'd be very expensive. So another decision matrix here. The 3 options on the left. The geared motor scored way high again compared to these two, mainly because it was free. There was nothing that needed to happen with it. Basically, you have the motor. That's all you need. The belt drive scored low in design time and overall feasibility for the barn, when then the hydraulic ram scored very low because of its price, and it would be too large for the barn. So if the geared motor had not have been donated, it would have scored lower. It would have scored a 58 compared to a 63, but even so, it still would have been the most feasible option for the barn. Here's Colin to talk about the design process.
Since we've all heard so much about SolidWorks this afternoon, we're going to make this as brief as possible. SolidWorks is a computer-aided design program, or CAD program, used for designing and modeling parts of our project. This is a drawing that SolidWorks produced for us that we can then take in the machine shop and use to produce our parts. This is a quick model here. You can see our alley scraper sliding down the center of the alley on the red I-beam there. Gets to the end there, hits a limit switch, the arm retracts due to friction, and slides back along the I-beam.
In our project, we did not have any big structural loads that required us to utilize a finite element analysis. This video shows a nonlinear transient analysis of an engine assembly and other structural analysis with large displacements, rotations, and surface contact. As you can see here, we have plastic deformation in each corners of the box cylinder being closed. After my group and I have all agreed on mechanical design, we now have to reach past our comfort zone and design this electrical system around a generator power supply that the owner will be providing. After hours of research, I was directed to speak to Professor Correa about a possible electrical design to utilize. And this is the electrical schematic that worked for our design. After we settled the design and hours of learning what everything in the schematic means, it was time to test the circuit before ordering parts. The parts in this video, were graciously donated by the electrical department. As you can see here, in this video, this is the Mach-Connect electrical analysis. The start button is hit, the motor starts, the first limit switch is hit, which reverses the motor, and the second limit switch is hit, which stops the motor. Start switch hit, motor starts, reverse, and stop. After we ran this successful analysis, we then began to order parts, and this is where we started. We have a limit switch, 2 limit switches, a control box, and 2 relays. Here's a video of our prototype in full operation utilizing our electrical components. As you can see, the motor started. The first limit switch is hit, stops the motor, and is held for 4 seconds or longer, and then reverses the direction of the motor until our scraper reaches its home position and hits the second limit switch, which will stop the motor. Before the final product became what you see here, Professor Correa and I have spent numerous hours analyzing the system, just to find many problems. In addition of a timer relay, this white box here was required in order to stop the motor completely before reversing the direction of the motor. If this motor does not come to a complete stop before reversing, it would have blown our control box. Also, a 240 volt transformer was utilized to power our electrical components. This transformer breaks down the 240 volts AC current into 24 volts DC voltage. And this was due to the electrical components needing to have a low voltage near the live stock. Also, safety fuses for the 240 and 120 volts AC were also utilized. I would like to give a special thank you to Professor Correa for his dedication to his job by teaching and guiding me in the right direction for our electrical system. Professor Correa has dedicated over 15 hours of his own personal time to help. Please, if you will, join me in a round of applause for Professor Correa.
So SolidWorks also helped us to do the rest of our design work. Here you can see our alley scraper with our limiter chain in place. The limiter chain is pretty much just to hold